Welcome to another video for AP Statistics. In this video, we're going to talk about how to calculate a confidence interval for a population proportion. This deals directly with inference for data. Now, what is inference? So keep in mind the procedure and methods of making a judgment about a population parameter based on a sample statistics. That's what inference is. We want to make a judgment about a population proportion, and we're going to do that by getting a sample proportion and using that sample proportion to make a judgment about that population proportion. But in order to make a judgment about a population proportion, we first need to know that population proportion. So then we could say, hey, I think it's more, I think it's less, or I think it's perfect. But what if we don't even know what the population proportion is? How could we make a judgment about a population proportion without even knowing it? Well, I guess we could start with a sample proportion. That's exactly where we are going to start. We're going to learn in this video how to use a single sample proportion to help us make an estimate for what the population proportion could be. Now, let's not fool ourselves. We should know by now that a sample proportion is not going to match the population proportion exactly. It should be close, but it's not going to match it perfectly. Why? Because samples vary. And there's only one true population proportion where there are many and many and many and many and many sample proportions. And there's no way that all those sample proportions are going to match the true population proportion exactly. So this is where we actually have to bring in the concept of a sampling distribution. A sampling distribution is actually going to show us what all possible sample proportions would look like. So let's keep in mind what a sampling distribution looks like. First, it has a center. It would be the mean of all possible sample proportions. And you would assume if you looked at all possible sample proportions, the mean of them all would be the truth right smack dab in the middle. Again, it would make sense that 50% are going to be more than the truth, 50% are going to be less than the truth, which is going to put the truth right smack dab in the middle. But we also have this very strong understanding that sample proportions do in fact vary. So of course there's going to be a standard deviation, which we've learned a formula to find that standard deviation to estimate how those sample proportions will vary. So we calculate that standard deviation using the true proportion P, and then the opposite, 1 minus P. And once that's calculated, we could look and see that, hey, a sample could be a little higher, or even really, really high, going up 1, 2, 3 standard deviations. And then same thing going down 1, 2, 3 standard deviations. Okay, makes sense. So a sampling distribution is absolutely positively filled with tons and tons and tons of P hats. It's going to show us what all possible P hats look like. Now, here's the key. I don't know the truth. I don't know the truth, right? That's the whole point of this video, is we don't know what the true population proportion is. We're trying to find out what it could be. Now, if I grab a sample proportion, then maybe I find out that I fall right here. A little bit on the low side. Well, first, is that okay? Well, listen, samples vary, so it's no wonder that I didn't find P. I got a little bit lower, but I could get another sample and it may be a little bit higher, or another sample that's just a smidgen lower, or it would be weird, but I guess it would not be impossible to get a sample proportion way over here. But again, this is the whole point of what sampling distributions show us. So I say, let's go fishing, right? We're trying to catch the true P. And if I just look at a single sample, I'm probably, let's put it this way, I'm not confident that I'm going to get the exact truth because I know that samples vary. But I do know that if I go fishing looking for that true proportion and I collect a sample to do that, I bet my sample will be close. Let's dive into this a little bit further here. So right smack dab in the middle is the true proportion that unfortunately I don't know. I'm looking for it. But here's what I do know, right? For example, I know that 90% of samples are really, really close. Now, let's figure out a z-score that actually represent that 90%, right? We could go and grab our calculator. And we could, if you have a TI-84 calculator at least, that's what I'm going to show you here, go to second vars, and we see number 3 there is an invert norm. Now, invert norm will give you a z-score with a percentage either left, right, or in the center. So if you do have the center command, you could type in 0.90 and make sure you go down and select center. So this is going to give us z-scores that represent that middle 90%. Okay, so that gives me a z-score of negative 1.645 to positive 1.645. So somewhere right around here, negative 1.645 to right about here, positive 1.645. Now, if you don't have that left, right, center feature on your calculator, let me quickly show you what you'd have to do here. Older versions of the calculator always are set to left. Like you literally can't change it, it's set to left. So here you'd have to do a little bit of thinking. If we're looking for the 90% in the middle, then that would put 5 at the bottom to the left and 5 at the top to the right, which would leave the 90 in the middle. So if I have a calculator that's set to only left and I don't want to change it, or I literally can't change it, then I'd have to do the bottom 5%. And that bottom 5% would produce that negative 1.645. And I would have to know, due to symmetry, the top would be positive 1.645. So what am I trying to get at here? Well, that means that 90% of samples, 90% of p-hats are going to be in that middle 90%. So that means that if I were to go and just grab a p-hat, I'm 90% confident it's going to fall somewhere in this range with a z-score of negative 1.645 to positive 1.645. Now, maybe it's here. I don't know. Maybe it's here. Maybe it's here. Maybe it's here. Maybe it's here. But I'm 90% confident that since 90% of samples are within this range of z-scores, I'm 90% confident that my p-hat is going to be in there. Now, it's not going to be equal to P, so I don't want to ever claim that my p-hat is the truth. No, 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 no. That would be very foolish. But check this out. Check this out. If I do find this p-hat right here. Now, I didn't even know it was on the low side because remember, I don't even know what the true P is. But if I had the model, I would know it's on the low side. But again, I don't even know that. But if I took my p-hat and I built an interval, if from my p-hat I went up 1.645 and down 1.645, I would create an interval. And the truth was in my interval. So I don't know exactly what the truth is because, come on, p-hats aren't going to match up P exactly. But if I built an interval around my p-hat, by going up and down this 1.645 standard deviations, then I could create an interval, low over here to high over here, where I would be 90% confident that the truth is in. It's in there somewhere, right? And notice it did catch it. And I could just do another example here. I'll grab another color just to kind of show. Let's just say that my p-hat was right here. Now it's on the high side, but again, I don't even know what the truth is, so I didn't even know I was on the high side. But if from that p-hat I go down 1.645, up 1.645 standard deviations, I create an interval, low to high, that, hey, in that interval, the truth was caught. So that's what we're doing. We're going fishing, right? We have one sample proportion, and we first know that it's not going to match the truth exactly, because, come on, samples vary. But if we cast a net around our p-hat by going up and down a certain number of standard deviations, then we would be pretty confident that we would catch the true proportion within our net. Just to kind of give you one more example, I just really want to hit home. Even if I caught a sample that was up here, the point is any sample that's in the 90% window, if I catch or create an interval up 1.645, down 1.645 from that p-hat, since that p-hat started in the 90% window, the truth should be caught in its interval. Now, I do have to play kind of devil's advocate here for just 1 second. I know my screen's getting a little bit messy, but if, let's just say that I did get a p-hat down here that is outside of that 90% window in the middle, then I would run into a problem. Then when I go up 1.645 and down 1.645 in my interval low to high, I did not capture the truth. The truth right here was actually not in my interval. But again, that's why I'm saying I'm only 90% confident that the truth is going to be caught within my interval. Let me do one more example here. Let's actually up it, right? 90% is pretty good, but let's be 95% confident. So once again, this starts off with a sampling distribution where we know the truth is in the middle, even though we don't know exactly what that truth is. We know that it does exist. So if I want to look at 95% of samples, I do have to grab my calculator one more time. So again, if you have this center feature, I chose the wrong one there. Sorry about that. Second vars, go down to number 3. If you have the center feature, you can actually put 0.95. It'll give you the z-scores that represent that middle 95%. But if you don't have that and you only have the left command here, then we're going to do 0.025. Because again, 95% is in the middle, and I only need the point on the left, or the area to the left. So 95 is in the middle. That puts 2.5% to the left. Okay, and that would also put 2.5% to the right, which would be the top. So this gives me a z-score, and if I round that correctly, negative 1.96, if I actually round that correctly. So that would mean that anywhere from negative 1.96 to positive 1.96, this would be 95% of samples. So once again, I'm 95% confident that if I find a p-hat, it's going to be in that interval. It's going to be in that 95%. Because again, 95% of samples are going to be within that range, so why wouldn't mine be? Now, again, I'm understanding that that p-hat is not going to match the truth, but if I put an interval up 1.96, down 1.96 from my p-hat, then I'm 95% confident that the truth will be caught within my interval. So the basic idea is this. We're going to start with a sample proportion. We're going to add and we're going to subtract a certain number of standard deviations. And again, how many standard deviations do you add or subtract based on how confident you want to be? Back here, I was 90% confident. That was a z-score of positive and negative 1.645. Here, I want it to be 95% confident, so that's going to be a z-score of 1.96. Now, that is not 1.96, that's 1.96 standard deviation, so I do need to calculate my standard deviation, but that's actually where I run into another problem, but not a big deal, as I'll explain. The idea is I actually don't know my standard deviation because the standard deviation formula requires the true proportion P, which I unfortunately don't know. So we're going to do something that's really kind of weird here, very kind of different, but just bear with me. We're not going to find standard deviation because, again, I hope you understand I can't. If I don't know the true proportion that's in the center, because that's what I'm trying to find, then I certainly can't calculate the standard deviation because I need the proportion for the standard deviation. So what I'm going to do here is I'm going to do something that's going to seem a little bit weird, but I'm going to replace P with P hat. Now, if you've watched some of my other videos, I've actually said to not do this, but I'm going to still do it anyway. So I'm going to replace P with P hat because, again, I am using P hat as an estimate of what that true proportion could be. Now, the only problem is I'm not allowed to call this standard deviation because I'm changing the formula. Like, I'm literally changing the formula. So I'm going to call it something else called standard error. I'm not calling it standard deviation. I'm calling it standard error of my sampling distribution. Think of it like the twin brother of standard deviation. Same formula, just replacing the P with P hat. But it's not the same, so I have to call it standard error instead of standard deviation. Hopefully that makes sense. So now the idea is, like I'm saying here, if I go ahead and start with my P hat and I create this net by going up and down 1.96 standard errors. Let me rewrite this. It would be P hat plus or minus 1.96 times the standard error of P hat. Now, that standard error, again, comes from my P hat value. Okay, so we'll explain that a little bit more in a moment here. That will create an interval where I'm 95% confident the truth is. So again, it's creating, it's this idea, very simple, very common sense idea, that I do not know what the truth is. But I do know a sample proportion should be close. And in fact, it should be so close that if I create an interval by going up and going down from my sample proportion, the truth will be caught in my interval. I do have to say for the second time, we're not 100% confident, because there is the possibility that you get a sample way down here. Those samples are very weird, very rare, but you could get them. They're not impossible. And when you create your net by going up and down, notice what just happened. I did not capture the truth in my interval. That does happen, which is why I can never say I'm 100% confident that the truth is in my interval. All right, let's actually walk through an example here so you can see how this is actually going to play out in a real example. So Justina, who is lactose intolerant, she wants to know the true proportion of all residents in her hometown of Twinsburg, Ohio, that are lactose intolerant. She literally has no idea what the true proportion is, doesn't even know where to begin. So to try to get an estimate, she gets a random sample of 450 residents. In fact, it's a great sample. It's stratified. It's got some old people. It's got some young people. It's got different ages, different ethnicities, different genders, different eating habits, different exercise habits. I mean, it's just the creme de la of samples, right? Okay. And in her sample of 450 residents, she found 171 that do, in fact, admit to being lactose intolerant. So if I take that 171 and I divide by 450, I get 38%. Now, can she officially say that the truth is 38%? Absolutely not. Because we know, based on variability, that the value of p hat will almost never equal the value of p. It should be close, but I have no confidence that my p hat is going to match the population proportion exactly. But to increase our confidence that our estimate is close, we could use an interval. Again, starting with our p hat and wrapping an interval around it with where we think the truth is. So once again, Justina has no idea where the truth is, and she did find a sample proportion of 38%, but she doesn't even know if that's high or low. We literally have no idea. Let's just pretend for a second that it fell right here. Well, if she takes her sample, goes down and up by creating an interval, she should be confident that the truth is in her interval, which here it was. Again, let me just do another example. Even if her sample was down here, when she creates her interval by going down and going up, oh my gosh, she captured the truth in her interval. That's the concept here of a confidence interval. So a confidence interval in AP statistics, we abbreviate it with a CI for confidence interval. It all starts with taking a point estimate. A point estimate is a sample proportion or a sample mean that we'll see later on in other videos. But for right now, a point estimate is literally just the estimate that she found in her sample. And we add and we subtract what's known as the margin of error. Now, the margin of error is a combination of two variables. It is the critical value, which we'll talk about in a moment, times the standard error. And that's that standard error I already talked about. So let's dive into that standard error one more time. We should be going up and down standard deviations. But remember, as I've mentioned earlier, the formula for standard deviations involves knowing the true proportion of people that are lactose intolerant in Twinsburg, Ohio, but Justina has no idea what that is. All she knows is her p hat. So if we replace the p's with p hats, we get the same formula, but we do have to call it standard error. Again, it's the twin brother. It's the best estimate that we can do because, unfortunately, we just can't use standard deviation. Now let's talk about that critical value. This is what I already mentioned. If we want to be 95% confident, that's a critical value of 1.96. Again, where did I get that from? 95% confident means that we're looking at the middle 95% of all possible samples. And if you have the feature to select center, I selected the wrong thing again there, sorry. Then you could definitely type in 0.95 into invert norm and you'll get the 1.96 and positive 1.96. But if you're like me or you just have it stuck on left, then remember you do have to do a little bit of thinking there. 95 in the middle puts 2.5% at the bottom, 2.5% at the top, and invert norm without this tail feature only cares about the bottom. So that's another way that we could get that 1.96. And we know that it's going to be negative on the left, positive on the right. That's how we get that critical value. We actually call this a Z-star. It's a very special Z-score specifically for a level of confidence, in this case, 95%. So that's it. This is how simple it is, right? We're gonna take our statistic. That was our point estimate. Now remember, for Justina, that was 38%. That's what her sample showed. We're gonna go up and we're gonna go down. Now, if we want to be 95% confident, that's that 1.96. Now the negative and positive is accounted for right here with the plus or minus, because we're going up and we're going down. And Justina's standard error is going to be the square root of 0.38 times 0.62 divided by the 350 people in her sample. So if I go to my calculator, I can actually calculate my margin of error. 1.96 times the square root of 0.38 times 0.62, that's just the opposite of the 0.38, divided by my sample size of 350. And we get, oh, wait a minute, I apologize. I'm going to just go all the way back here. I so apologize. It was 450 people. My fault, 450 people. That's actually better, right? Bigger samples are better. So let me come down here real quick. Let me change this to 450. And I am lucky I didn't hit enter yet. I knew something seemed fishy there. Oh, I did hit enter. Dang it. Okay, so let me go back here, change that to a 4. Thank you for being patient with me. And there we go. I hit it 3 times. 0.0448. So if we take that 0.38 plus or minus 0.0448, now we could create an interval. And again, so I got to go up and I got to go down. So 0.38 minus the 0.0448, and then 0.38 plus the 0.0448. And an extra 4 there. This thing is super sensitive. There we go. So an interval of 0.3352 to 0.4248. 0.3352 to the top of 0.4248. 0.4248. So here's the idea. Justina came into it having no idea what proportion of people in Twinsburg were lactose intolerant. Her sample showed 38%, but that was just an estimate. So she went up and down by a margin of error, and now she's 95% confident that somewhere between 33.52% and 42.48% of residents are lactose intolerant. So I'm 98. So here's my conclusion. I'm 95% confident. I can't say I'm 100% confident because there is a chance that she got a weird sample whose interval does not contain the truth. So please understand that. She's 95% confident the true proportion of people that live in Twinsburg that are lactose intolerant is somewhere between, again, 38.52%. And the other one I got was 42. Boy, I'm having a really tough day here. It was 33%. See, go to my calculator there, 33.52%. And then 42.48%. All right, so there we go. That's it. Pretty simple, not overly complicated here. Now, I really want to emphasize what 95% confident means, because this is that kind of like a big question. A lot of kids don't quite always understand it. It all starts with that sampling distribution. Even though I don't know the center of the sampling distribution, which is the truth, I still know, no matter what, that 95% of samples are within that 1.96 to positive 1.96 z-score, right? So I am confident that my sample is one of those, right? 95% is a lot, right? So as long as my sample is one of those many samples that's within that 95% window, then my interval will contain the truth. So go back to this picture here. It's like a betting game, right? I'm betting that my p-hat is somewhere in this interval. I don't even care if it's high, low, kind of low, doesn't even matter. As long as I'm in that interval, or in that middle 95%, when I create my interval by going up and down, I will contain the truth right smack dab in the middle. Not the middle of my interval, but somewhere in my interval. So that's the idea of why I'm 95% confident. And if you only want to be 90% confident, what you have to adjust is your z-star. All right, so here is a quick rundown of actually how to do this. The official name of what we're learning right now is a one sample z interval for a population proportion. So step 1 is actually saying that name and identifying what you're trying to find. So Justina would say, I'm doing a one sample z interval for the population proportion of Twinsburg, Ohio that is lactose intolerant. The name is really important as well as the context. Now, even though we're not actually building the sampling distribution because we can't without knowing the true proportion in the center, we still are relying on the existence of that sampling distribution to understand what's going on here. So we still have to check the conditions for that sampling distribution to be normal. We have to make sure our samples are random to avoid bias. We have to make sure our sample size is under 10% of the population to assume independence. And we need to make sure we're big enough. That means we need to have 10 or more successes and failures within our sample. Then step 3 is the fun part. This is where we're actually building our formula here. This formula is taking that estimate of p hat and going up and down by that margin of error. Again, that margin of error is a combination of a critical z star that is fully based on how confident you want to be, multiplied by, oh boy, it looks like the standard deviation formula, but remember, that's actually the standard error formula. It's okay. And then step 4 is our conclusion about, hey, I'm 95% confident that the true proportion I'm looking for is somewhere within this interval. So at the end of the day, we have 4 pretty simple steps. The concept, I hope, makes complete sense. I'm trying to find the true proportion. I'm going to estimate what the p hat. The one thing that is a little bit weird that might take a little bit of time to get used to is this whole idea of confidence. But again, it all comes back to that sampling distribution. Even though I can't build it, it does exist. And I'm very confident, 95% for this particular case, that my sample is somewhere in the middle. Hence, the true proportion is close to me. Now, obviously, a bigger sample is going to help, right? Because a bigger sample is always going to make a smaller standard error. Well, in this case, standard error, same thing as standard deviation, right? And when you have a bigger sample size, you're always going to be closer to the truth. Let's look at one more example following all 4 steps for all of this to really kind of hit home. Marine biologists have been noticing more and more aquatic sea fans that are becoming infected with a bacterial fungus that is causing the sea fans to die off in extreme numbers. To estimate the proportion of infected sea fans, researchers select a random sample of 55 sea fans. There's my sample size. And of those 55 sea fans, 12 are infected. That's going to produce my p hat. 12 out of 55, if you need a calculator, grab one, is about 21.8%, 0.218. Now, create a 95% confidence interval to estimate the population proportion. Just for sake of doing something different, I'm going to actually do a 90% confidence interval, just to kind of show you how that's actually going to change my critical value. I just want you to be aware of that. All right, so first I have to admit that this is not the truth. It's just an estimate of what the truth could be. But if there was a sampling distribution out there, boy, that is a terrible normal model, somewhere in the center is the truth, and I'm just going to bet my money, I don't have a lot of it, but if I had some, I would bet that my sample is somewhere very close to the truth. And if I built an interval around my sample, I'm hoping to catch the truth. So here I go. Step 1, I will estimate the population proportion of infected sea fans in the Atlantic Ocean with a 1 sample z interval for a proportion. You could also say that in reverse. This is a 1 sample z interval for the population proportion of infected sea fans in the Atlantic Ocean, as long as you have the context and the name. Step 2 is the conditions, because we are understanding a normal model exists for that sampling distribution, so we do have to check our conditions. Sample was random to avoid bias. There's tons of sea fans in the Atlantic Ocean, so I'm confident 55 is less than 10% of all of them. And my sample had 12 that were infected, leaving 43 that were not infected, both larger than 10, so that normal model can be used. Now here comes my work. Now, this work is for 95%, but again, and I'm going to stick with that, but I actually want to show you if I want to be 90%, or we can even do 99%, how that's going to change. I'll show you that right now. So once again, the formula, pretty simple. Start off with our p hat. Our p hat was what our sample showed. I actually kept one more decimal there just for accuracy. Then let's talk about standard error. That's this back part here. So it's the same formula as standard deviation, but because I'm using a p hat instead of p, I have to call it something different. That's why I'm calling it standard error. Now let's talk about the 1.96. If I was being 95% confident, that puts 95% in the middle. Boy, oh boy, that's the 3rd time I messed that up. Second, vars, number 3, invert norm. If you have the command to do center, please use it. 0.95 is the area, and then select center. But if you don't have that, then you got to go to the left, because that's what it would automatically be set to. And if you're 95 in the center, that puts 2.5% to the left and to the right, which produces a z star of 1.96 and positive 1.96. But if the problem said 90%, right? 90% is a little bit worse, but okay, whatever. Then I would have to put 90% in the center, or 5% to the left, right? 5% to the left, 5% to the right, 90 in the middle. It's all the same thing. That would be a z-star of 1.645. Or let's just say we want it to be 99% confident, right? Okay, let's walk through this. 99% in the middle, put 0.99 and select center. Or that would be 0.5%, 0.005, that's 0.5% to the left. Because if there's 99 in the middle, there's 0.5 to the left, 0.5 to the right, 99 in the middle. So that would be a z-star, a critical z-score of 2.576. Notice it gets wider. So if you want to be more confident, you do have to be wider. I mean, that makes more sense. If you want to be more confident to catch fish, just make a wider net. Come on. So with more confidence does come a wider net. So that's just going to change your z-star. That will not change your p-hat. Your p-hat is what it is. That will not change your standard error. But based on how confident you want to be, will change your z-star. Anyway, multiply the z-star times your standard error, get the margin of error, add and subtract that to get your confidence interval. Finally, step 4, I'm 95% confident that the true proportion of infected sea fans in the Atlantic Ocean is somewhere between 10.9% and 32.74%. Again, I'm admitting I don't know what the truth is, but I'm very confident it's somewhere in this interval. Now, you might say, hey, that interval's kind of wide. Like, what kind of interval? 10% to 32%? That's a pretty wide interval. So how could you make a smaller interval? Bigger sample size. A bigger sample size is going to be more accurate. It's going to produce a smaller standard error, which is going to produce a smaller interval. So come on, get more sea fans, get a sample of 200 sea fans, and you're only going to get a more accurate interval. All right, that's it for confidence intervals. I hope that I did a good job explaining the concept of them and doing a couple examples so you could see how the 4 steps work out. All right, see you later.